And this is the solution. These huge, sprawling, incredibly complex industrial plants are designed to solve that exact problem. They take that cloud of natural gas and they transform it into something dense, something stable, and most importantly, something transportable. And the secret? They make it unbelievably cold.
Now, this is the part that's just wild. When you chill natural gas down into a liquid, its volume shrinks by a factor of 600. So, to put that in perspective, that's like taking all the air inside a massive concert hall and squeezing it all down into a single shipping container. This incredible volume reduction, that's the key. That is what unlocks global transport.
So here's our game plan. First, we'll look at the core problem of moving gas around. Then we'll get into step 1, purification. After that, we hit the big chill and explore the 3 main recipes for liquefaction. And finally, we'll look at the final product itself, LNG. You see, for decades, the simple fact that natural gas takes up so much space meant it was basically stuck on land. Sure, you could move it through high-pressure pipelines, but putting it on a ship to cross an ocean just wasn't economical. This pretty much limited natural gas to being a regional fuel, connecting producers and consumers with fixed pipelines. But liquefaction? Well, that changed everything. Okay, so how do they actually do it? Well, the very first major step before a single bit of chilling happens is purification. You just can't take raw natural gas from the ground and cool it. It's full of all kinds of impurities that would just wreak havoc on the multi-billion-dollar equipment in these plants. Think of this pre-treatment process as a kind of gauntlet the gas has to run through. It starts with the raw feed gas coming into the system. Then it gets sweetened to pull out all the acidic gases. And finally, it's dried to get rid of every last drop of water. Only after it passes these 3 stages is it pure enough for the deep freeze. So what are we actually trying to get rid of? Well, the main culprits are carbon dioxide, hydrogen sulfide, and plain old water vapor. And that hydrogen sulfide is a big one. In fact, natural gas with a lot of it is often called sour gas because of its nasty, rotten egg smell, and getting rid of it is absolutely critical. Now, the process of removing these things is called sweetening. And look, this isn't just about efficiency, it's a huge deal for safety and protecting the equipment. Hydrogen sulfide isn't just highly corrosive to all the pipes and machinery, it's also extremely toxic to people, even in really tiny concentrations. And what about the water? Well, at the crazy cold cryogenic temperatures we're about to get to, any water vapor in the gas would instantly freeze solid. It would form these ice-like structures called hydrates, and these things would act like cholesterol in an artery, just clogging up the pipes and bringing the entire plant to a grinding halt. So getting the gas bone dry is totally non-negotiable. All right, so our gas is now clean, it's dry, and it's sweet. Now we can finally move to the heart of the whole operation, the big chill. This is where the real magic happens, using the principles of refrigeration on a massive, massive industrial scale to get to some just mind-bogglingly low temperatures. And here it is. This is the target temperature. To turn natural gas, which is mostly methane, into a liquid, you've got to cool it down to about minus 160 degrees Celsius. That's minus 256 Fahrenheit. To put that in perspective, that's colder than the harshest winter day ever recorded in Antarctica. We're in the world of cryogenics now. The technology behind all this is basically a supersized, superpowered version of your home refrigerator. It uses a special fluid, a refrigerant. First, you compress that fluid, which makes it really hot. Then you cool it down, and after that, you let it expand very, very quickly, which makes it intensely cold. That cold is then used to chill the natural gas. Simple principle, incredible scale. So while the principle itself is pretty simple, actually using it to hit minus 160 degrees Celsius efficiently, well, that takes some really clever engineering. Over the years, engineers have developed 3 main recipes, or technologies, to pull off this big chill: the cascade cycle, the mixed refrigerant cycle, and the expander cycle. First up, we've got the cascade process. And you can think of this one as teamwork. Instead of one huge cooling loop, it uses several smaller ones in a series. You can see in the diagram here how a propane circuit does the first stage of cooling. Then a colder ethylene circuit takes over. And then finally, a methane circuit comes in to finish the job. The graph on the right shows it perfectly. You can actually see the temperature dropping in these distinct steps with each stage. All right, the next recipe is the mixed refrigerant, or MR, cycle. This one is a bit more elegant. Instead of having all those separate loops, it uses just a single loop that's filled with a very carefully blended cocktail of different refrigerants, things like nitrogen, methane, ethane, and propane. This special mix evaporates at different temperatures along the way, which creates a really smooth and highly efficient cooling curve. And finally, we have the expander cycle. This one is really clever. It actually uses the physics of the gas itself to create the cold. The pre-chilled natural gas gets sent through something called a turbo expander, which is kind of like a turbine running in reverse. This makes the gas expand and its pressure drop all of a sudden. And that rapid expansion causes such a massive drop in temperature that a portion of the gas just instantly liquefies. Now, in the real world, these plants don't always just pick one recipe. They often mix and match them to create these super efficient hybrid systems. This table here shows some of the most popular licensed technologies out there. You can see they're categorized by how many cooling cycles they use and what kind of refrigerants are inside them. For example, the super popular C3MR process combines a simple propane loop for the initial pre-cooling with the more efficient mixed refrigerant loop to do the final deep freeze. It's the best of both worlds. So, after all of that cleaning and all of that chilling, what are we left with? Well, we've successfully transformed a high-volume, unruly gas into a low-volume, stable liquid. This is our final product, and it's all ready for the next leg of its journey. The result is liquefied natural gas, or LNG. It's stored in these giant, heavily insulated cryogenic tanks before it gets loaded onto specialized LNG carrier ships. It's now officially a global commodity, ready to travel the world and hit the open seas. And that right there is why this whole thing matters so much. This is the technology that created a truly global market for natural gas. It allows countries that have a ton of gas resources to sell it to countries that desperately need energy, no matter how far apart they are. It fundamentally completely redrew the world's energy map. So we've seen how this incredible feat of chemical and cryogenic engineering really works. But as with any major technology, solving one huge problem often creates a whole new set of questions. This process absolutely unlocked global energy markets, but it also leaves us to think about what new challenges does it create for energy security, for infrastructure, and for the environment.